Now that we have carried out feed-forward process, wherein all the data we have inputted to the neuron after processing, after mapping it in between 0 to 1 for each of the neuron, and processing it through various layers, finally reaching to output layer and comparing it with the target value, we have found out error as equal to summation 1 by 2 target minus the neuron output value y at output neuron square of that, right? Now we want to minimize the error, and error as of now we know to be dependent on this weight or this weight and every weight in the previous layers. So right now the error here will be focusing only on this part, will be differentiating error with respect to weight in between these two neurons. Okay, what we do in for this weight will be equally applicable for this weight as well. So we'll be differentiating error DE with respect to the weight in between H21 out. This is H21. H21 means the first neuron in second layer, and out means there are two parts of this neuron. The upper value we are calling as in value, H21 in, and the lower one we are calling as H21 out. What is the difference between H21 in and H21 out? H21 in is the value of this new value at this neuron after we do sum of the product of H neuron value, out neuron value at each of the neuron in previous layer multiplied by the weights coming to this particular neuron. That is H21 in, and after we process this H21 in by sigmoidal function, what we get is called as the H21 out. That's clear, I think. Okay, H21 out. So H21 out to O1, that weight O1 in, you may call it O1 in rather. Yes, it is O1 in. O1, if you find in this expression only O1, that you take it as O1 in, right? So we have to differentiate error with respect to this particular weight. So you have understood what that weight is being talked about. Subscript here is telling you, is specifying the weight to you. Okay, it is connection between H21 out to O1 in. Okay, now we will not be getting direct differentiation of error with respect to this weight, because there are some processes in between. What are those processes? The HO1 out is directly related. O1 out is basically Y. So O1 out is directly related with this error. This O1 out is related with O1 in, and O1 in is related with this weight and this weight. So if we take into account all these things, the differentiation of error with respect to this weight is to be obtained by chaining all these eventualities, all these things. Okay, so DE, we will be chaining the thing DE, differentiation of error with respect to O1 out. Okay, partial differentiation of error with respect to O1 out, then differentiation of O1 out with respect to O1 in, as you see here, and differentiation of O1 in with respect to this weight. So one by one, we'll be seeing the differentiation of this. It is not as complex as it looks. It is simple. Chaining you have understood, so you will be understanding the differentiation also. Now dE, we know it is one summation 1 by 2 t minus y square, right? So differentiation of this will be 2 into 1 by 2 t minus y into differentiation of y itself. Okay, differentiation of y will be minus 1. All right. So it will come t minus y is basically woven out into minus 1. So this is the differentiation of error. Okay, summation sign is implied there. Right. Now, uh, if you have different kind of error function, you will be differentiating that error function accordingly. Okay, this that is the that is why we are seeing the treatment of finding weight correction in this much of detail, because ANN provides you a lot of flexibility. You can choose error function, you can choose sigmoidal function, you can choose number of neurons, and where you have got a lot of flexibility in artificial neural network, so as to model your data by ANN. And it is for that flexibility the ANN has become popular. Various experiments with various things you can try with ANN, like error function you can take different, even the sigmoidal function right here. Second term now is dO1 out, partial differentiation of O1 out. Now just look at this cell. This part is O1 out and this part is O1 in. So differentiation of O1 out with respect to O1 in, it is how O1 out we are getting from O1 in by simply the sigmoidal function. For understanding the differentiation of that, I'll take you to next transparency, and once again I'll be coming back. Okay, in that transparency, I have detailed the differentiation process. Just to help you understand the differentiation process. So here D1 DO1 out upon DO1 in. Now what is how O1 out and O1 in are related? But they are related by this sigmoidal function 1 upon 1 plus e to the power minus O1 in. Now I'll be differentiating this. This is in fact 1 plus e to the power minus O1 in to the power minus 1, isn't it? So what will happen when I differentiate? That minus 1 will come here, and this bracket 1 plus e to the power minus O1 in into this bracket complete to the power minus 2 into differentiation of this, and that is what? Minus e to the power minus O1 in. Now, this again can be put back in terms of O1 out in this form: O1 out into 1 minus O1 out. Okay, you can take your time. Where in that you can put O1 out as this value 1 minus O1 out. You will finally get this, or you can come to this by simplifying this, by putting this in the formats of O1 out. So differentiation of O1 out with respect to O1 in is dependent on this sigmoidal function, and that for this sigmoidal function it comes out to be O1 out into 1 minus O1 out. Right, it's simple for this sigmoidal function, but soon the sigmoidal function change, this differentiation of O1 out with respect to O1 in will be different. It won't be O1 out into 1 minus O1 out. Right. So now that you have understood this, then coming on to the differentiation of this O1 in. Now again this part O1 in, differentiation of O1 in with respect to this weight, right? The weight between H21 out and O1 in. How they are related with each other? See, it is simply like the O1 in we are getting as the summation of 0.867, that I'll be saying as Mm, that I'll be saying as H21 out. This is H21 out multiplied by W21 out O1 in. plus H22 out into W22 out O1 in. That's I have detailed this thing in variable terms. Otherwise, you know this thing as a 0.867 into 0.35, 0.773 into 0.63. Only yeah, I have replaced this constant by their corresponding variables. Once again, I tell you what is this. This is H21 out multiplied by W21 out O1 in plus W H22 out multiplied by W22 out O1. Now, if I differentiate this with respect to W2 WH21 out O1, I will get first term, second term will be already, second term will get converted to 0 because I am taking partial differentiation, and in second term I have H22 out and W22 out O1. These are constants during that differentiation. Only variable is the W21 out. W21 out, O1 in. So its coefficient will be the differential of this term H21 out. Okay, this you will understand in next transparency. Once again, we will have one more opportunity to understand this. Okay. I have now detailed it by speaking, but next time when we will be coming across some term like that, it is well written and there you will understand it further if not understood here. Right? Now, these two terms are related with this neuron, and what are what are those two terms? One is minus t. That is the difference between these two, T minus O1 out. That is T minus O1 out, negative of this, minus of this, because it comes minus because of differentiation. All right. That is the term which you can attribute to this neuron, and another is O1 out into 1 minus O1 out. All these things you can concentrate, you can load to this neuron. Okay, because you know O1 out here, O1 1 minus O1 out is also known. Then T minus O1 out, this into minus 1, is also known to you at this neuron level. So we combine these two terms and we call that is the delta of this neuron. Okay, that is the delta of this neuron, and delta of this neuron you have to multiply it by this neuron's output value, H21 output value. To make this calculation simple, what you have to do, you have to find the error difference between target and output of this neuron, that is O1 out. That is one term, that is this one minus of that, and then another term is O1 out into 1 minus O1 out. That delta you will be getting at this node, and that you multiply by H21 out. That will be getting you what is called as correction on this weight. Okay, so this weight now will be earlier weight plus delta value which you have found out by this complete formula. That big delta has a small delta part which is to be attributed to this neuron only, and that is to be multiplied by H2 1 out here. Now, same way, if I want to talk directly, delta is already known here, and to get the correction in the weight, you simply multiply to that delta by this weight. What is that? H22 out. You will be getting correction. That correction is to be added to the existing weight. Now, it was fine for the outer layer. Okay. Now, if I come to correction of this weight, correction of this weight. Now, again this weight has some bearing with this error which we are getting here. So now what I'll be doing, I'll be differentiating this error with respect to this weight, with respect to this weight. See here what I have done. DE with respect to now what, the weight between these two neurons. How that weight is specified, how these two neurons are specified, that is H 11 out, uh, H11 out, H21 in. Out of this will be connecting to in of this. H11 out to H11 out to H21 in. That is the weight. Okay, so we want to have just one sample weight I am taking to get the methodology by which I'll be correcting this weight, and once I get the methodology, I can implement that methodology to all this weight in this layer, and by doing that, I will be knowing what I have to do with this previous layer. Now, next time I won't be differentiating this weight with respect to this error. Okay, by doing my process with with this layer, I will come to know, I will get hold of the methodology. Okay, so for that I'll be just analyzing, I'll be taking the differentiation of the error with respect to this weight, and this weight is specified by H11 out, comma H21 in. The term sounds bigger, but you understand that is simply the address. The suffixes are the address of the connection start and connection end. Now again, you won't be directly getting the differentiation. The differentiation you will have to chain. Okay, just see how do I chain it. I'll be taking the differentiation of this error with respect to out of this O1. Okay, differentiation of error with respect to O1 out. Then O1 out I'll be differentiating with respect to O1 in. Then O1 in I'll be differentiating with respect to H21 out. H21 out. Okay, I'm not taking this weight in between in the other part of the chain. Okay, Uh, so H21 out will be, sorry, O1 in is to be differentiated with respect to H21 out, and then H21 out will be differentiated with respect to H21 in. Okay, and H21 in will be differentiated finally with respect to this weight. So that now what happens, this O1 out gets cancelled, O1 in, O1 in, then H21 out, H21 out, D H21 in and DH21 in gets cancelled to get finally get me the thing of my interest. So I want to find out differentiation of error with respect to the weight, hmm, this weight. Okay, the address, starting point of which is this neuron and ending point of output of this neuron, and ending point is input of this neuron. Okay, so let us find them one by one. DE by differentiation of error with respect to D1 out. Okay, so for this, because most of the term involved in this expression, in this equation, are mostly dealt in the next transparency, except for the last term. Okay, except for the last term, so it will be that transparency will help us in getting the differentiation of these terms. Okay, at least one, two, three, four terms. There are five terms involved in the chain. Fifth term we will be seeing the differentiation, mm, just as normal as we have seen in this case. Right? So here it is. This is, however, the differentiation of error with respect to threshold value at H21. However, we are dealing with differentiation of error with respect to this weight. That is the difference between what we have to see and what we are seeing. So DE upon DO1 out. This we have already seen, but just to help you understand it again, E is summation. Summation sign I have not written here. Summation 1 by 2 T minus O Y out square. Okay, differentiation of this along with summation sign will be coming at this 1 by 2 multiplied by 2 multiplied by t minus y1 out multiplied by differentiation of this, that comes equal to minus 1. All right, and then coming on to second term. So coming on to second term that we have already seen, and in that term, differentiation of O1 out to with respect to O1 in, it is simply just we will have to consider the relationship between O1 out and O1 in, and that is sigmoidal relationship. O1 out we get from O1 in by processing O1 in by a sigmoidal function, and by differentiating we finally end up getting O1 out into 1 minus O1 out, that we have seen in detail. Now coming on to the next term, and that is O1 in with respect to H21 out. Now just look at it. O1 in is this, the first half of this output neuron, and how it is related to H21 out. Okay. Now what happens? O1 in, O1 in here is coming out as the product of W21 out comma O1 into that is the weight, simply weight, that is this weight being talked about, into H21 out. That is the next half of this neuron, H21 out. Another part is not written here, but you can, because it differentiates to zero, we know very well, and I have discussed about it just when we were differentiating, when we were doing our previous differentiation. That another part that will be plus this weight multiplied by H22 out. Okay, so that part is not written here, but you read that here, that will be here. So we'll be differentiating this with respect to WH21 out O H21 out O1, that is coming out to be what? That is coming out to be um, this one, WH21 out O1. Okay, and W2H21 out O1. When we are differentiating it with respect to H21 out, this will be the differentiation, and when we are differentiating O1 in with respect to this one, this will be the differentiation. Okay, I hope you have understood this. And then coming on to H21 in, H21 differentiation of H21 out with respect to H21 in. Now we don't have to see this once again in detail. It is as good as seeing the differentiation of O1 out with respect to O1 in. Like it was O1 out into 1 minus O1 out, here it will be H21 out into 1 minus H21 out, because these two things are related to each other by sigmoidal formula. So the differentiation of H21 out with respect to H21 in will come equal to H21 out into, in bracket, 1 minus H21 out. And finally, this differentiation there, we were going to see it as DH21 in with respect to DWH21 out O1. Just a minute, I'll be taking you back to the previous slide. So, the differentiation of H21 in with respect to this weight, with respect to this weight we are talking, and W H11 out with respect to H21 in. All right. So, um, how to get the differentiation? Now we will have to find the relationship between H21 in and this weight. Right, h21 in is here, and this weight. In what way they are related? They are related in the way h11 out multiplied by wh1 out h21 in. Then here h11 out multiplied by W H11 out to H21 in. And lastly, I'm sorry, it will be H13 H13 out multiplied by W H13 out to H21 in, right? So when you differentiate this sum with respect to WH11 out to H21 in, as you had been seeing, or you can do it yourself, it will come H11 out, which is the coefficient of this weight in that summation. That will only remain. Other term will differentiate to 0 because they are constants with respect to this differentiation. So we get the differentiation of this complete term as this one. These two things we have already seen as the delta to be here. That is the error multiplied by O1 out into 1 minus O1 out has to be delta to be here. This delta we are multiplying by this weight as you are seeing here. Okay, and that will happen to be this delta multiplied by weight. That delta multiplied by weight we used to be multiplied by H21 out into 1 minus H21 out, and that is to be multiplied by H11 out. Okay, that is how we'll be getting the weight correction. Now what we will be doing, we'll be doing the little bit of simplification to get the delta value at this neuron. This total means this delta which we had at this neuron multiplied by this weight multiplied by H21 out into 1 minus H21 out will form to be delta value here, right? Will form to be delta value here, and delta value here will have to be multiplied by H11 out to get this weight correction. Right? Now, having understood this process, if I want to get the weight correction in this weight, what will I do? I have delta value here and I will be multiplying that delta value by this H12 H12 out value. Okay. So that is the advantage of having this combined into a delta value, having this combined into the delta value. So once I get delta value here, simply by multiplying this h1 2 out h1 3 out, I'll be getting the corresponding weight correction. Okay, so I hope this process is understood. But one thing need to be notified here, that you here there was only one weight. That's why it was point for us to get delta value here so easily. Simply what I did, delta value here multiplied by weight here, multiplied by H3 H21 out into H2 into 1 minus H21 out got me delta value here. But what if there are more than one weights coming, more than one connections coming at the neuron? Okay, so in that case what you have to do, you know the delta value here, you know the delta value here, and you know the delta value here. So what you do, you multiply this delta by this weight and this delta by this weight, sum them, you make the sum of this delta and w, coming from this side and coming from this side, and to that you multiply h21 out. In this case it will be h11 out into 1 minus h11 out. That will happen to be delta here, and this delta will have to be multiplied by h out here. That will be the weight correction here. H11 out here, H11 out here will be same value, because here we are not applying any what you say delta sigmoidal function. Okay, that will be giving you the correction here. So that is how the back propagation is carried out for correcting the weights, and weights are corrected by this new weight will be equal to old weight plus that the correction which you have got in each of the weight. Now finally what remains is threshold also is to be corrected. Okay, threshold is also to be corrected. Now what is the contribution of the threshold in the error has to be checked. So we have to differentiate error with respect to threshold here. So we'll be finding the differentiation of error with respect to threshold at 2 1. Okay, threshold 2 1. The subscript here I have written H21 just to locate the neuron H21, hidden layer 21 threshold at that point. Again, it is not directly related, so what we will be doing, we'll be differentiating E with respect to various events occurring in between. E will be differentiating with the output of this neuron DE by D01 out. Then O1 out will be differentiating with O1 in. Then O1 in will be differentiating with the H2 out, H21 out. H21 out will be differentiating with H21 in, and H21 in will be differentiating finally with theta value here. Okay, theta H21. All right. So this differentiation we have seen in detail, we have it already in detail on the next sheet. So till this point, till 1, 2, 3, 4 terms we have already seen. Only we were left to see, we were to see this last term. Okay. Now last term I have detailed out here. How do we get H21 in? Okay, that is the neuron value. Particularly I am talking about this neuron value, in of this neuron value, this is h21, and in part of this neuron value is the first part. Okay, if I divide this neuron into two parts, the first half will be h21 in, and another half will be h21 out, right? So this differentiation will be seeing how this H21 in is related with theta 21. Again, it is related by that summation formula, okay, which goes like WH11 out into H21. Sorry, weight, this weight I am talking about, WH21 out to sorry, WH11 out to H21 in, multiplied by H11 out. Okay, like here, then this weight, what is that weight? That is H21 out, H21 in, multiplied by H21 out. Okay, then H31 out multiplied by weight. What is that weight? WH31 out to H21 in. Okay, plus theta H21. All right. Now, if I differentiate this complete total, you can take your time by pausing this video and convincing to yourself about the relationship between H21 in with theta H21. Okay, there are other terms, but those are not important to us. because we have to differentiate H21 in with respect to H21 out. Others will differentiate to 0, because for that partial differentiation these all terms are constant. So this terms will differentiate to 0 and this will differentiate to 1. So finally what we get as the theta correction here will be same as this one, only last term will be 1. Okay, so this is how the theta will be corrected. So this process has given you an algorithm by which you will be correcting the weights. These formulas, once after deriving all these things, that lead to develop an approach by which the weights and thresholds will be corrected. Okay, so it starts from the last neuron and reaches to first neuron. It goes on correcting this weights, then thresholds here, then this weight, then thresholds here, then this weights, and that's it. And once this is done, again the forward pass will be taken. And now this time obviously it is expected that the error will reduce, but it won't come to the expected range of the tune of 0.01 or so. Again there will be error. Again this algorithm of back propagation will be followed, weights will be corrected, thresholds will be corrected. Again there will be feed forward pass, and again there will be backward propagation, again feed forward backward propagation. In all this process the weights will get corrected, thresholds will get corrected, and error will go on reducing, and finally it will so happen that the error is very less. Okay, and we say in that case the network is trained. Okay, this is exactly like when we get some kind of training. Initially there are going to be error when we start learning the car, or when, if you recall, when you learn recognizing the alphabets, might be that time it would have happened that you called D to B and B to D, or you have miscalling for the various alphabets. But you got trained again and again, that error back propagated, and again there was feed forward, again you went through the alphabets, again you have written the alphabets, but again you made some mistakes, that mistakes were pointed out to you, again back propagation was carried out. So this process of feed forward and back propagation make you perfect, trains your neural network, brings out the association between input and output. Now the training set which we have used for training this network, if you give different values within that envelope of data to this neural network, it will predict the value of output very precisely. Again, to what extent the neural network is trained, how good is the neural network model, how good, how well it is capacitated to predict the output, that is again measured by this RMSC and correlation, that is R square value. Okay, that is again measured by, you have know the actual values of y and computed values of y. Once this neural network is trained, then again your input is fed to it, and whatever the values of y you will be getting, in that case are called as computed values of y, and you already have target values of y. Based on these two columns, you can always find R square and RMSC. Okay, this is all about how to train the network. Okay, you may take the one more pass of your own through this video to understand this process very precisely. Thank you very much. We'll stop here. Thanks a lot.